Welcome student to my YouTube channel Bharat Chem Study. Today we are going to study about chapter 2 structure of atom for +1 class. In this video, that is part 3, we are going to study about atomic spectra, emission and absorption spectra, spectrum of hydrogen, Rydberg formula and numerical based upon it. So let's start with the topic. Spectrum or spectra. When white light from the sun is passed through a prism, it split into a series of colors bands known as rainbow of colors: violet, indigo, blue, green, yellow, orange and red, that we already have studied in our previous small classes, and they look like this one. The splitting of light into series of color band is known as dispersion, and the series of color band is called spectrum. In this spectrum there is continuity of colors, that is one color merged into the another without any gap or discontinuity, and such a spectrum is called continuous spectrum, which will look like this. So the color obtained by dispersion is consists of bands of color which are difficult to distinguish, therefore they can call it continuous spectrum. Now atomic spectra. Unlike the spectrum obtained by analyzing the sunlight, the spectra of atom are not continuous. The spectra of atom consist of sharp, well-defined lines or bands corresponding to definite frequency. There are two types of atomic spectra: emission and absorption spectra. So let's study them one by one. Emission spectra. Emission spectra are obtained when the radiations emitted from substances that have absorbed energy, either by passing electric discharge through a gas at low pressure or by heating the substance to high temperature and analyzing with the help of spectroscope. Atoms, molecules or ions that have absorbed radiation are said to be excited. For example, when the gases or vapors of chemical substances are heated by electric spark, light is emitted. The color of the lights depend upon the substances under investigation. For example, sodium or salt of sodium gives yellow light, while potassium or salt of potassium produce violet color. When the radiation emitted by different substances are analyzed, the spectrum obtained consists of sharp, well-defined lines, each correspond to a definite frequency, and are called emission spectra because they are obtained by the radiation emitted by the substance. Such a spectra consists of lines of definite frequency and is called line spectra or discontinuous spectra. For example, it look like, so here in this spectra you can easily identify that from where a color start and from where and at what position the color is going to be ended. So that's why these are called discontinuous spectra, because here the colors or bands are separated by dark gaps. Now absorption spectra. When a continuous electromagnetic radiation, say white light, is allowed to pass through a gas or a solution of some salt and the transmitted light is analyzed, that is remaining light is analyzed, we obtain a spectrum in which dark lines are observed in an otherwise continuous spectra. The meaning of this line is that because we are using white light, so we should obtain a continuous spectra, but because the substance from which the light is passed will absorb some of the part of the light, that's why we are getting discontinuous spectra. These dark lines indicate that radiation of corresponding wavelength has been absorbed by the substance from the white light. Such spectrum containing a few dark lines due to absorption of light and is known as absorption spectra. So here in this, a sunlight is passed through a solution of NaCl and then the transmitted light is observed. The absorption spectra look like this. Here you can see that instead of continuous spectra, there are certain dark gaps or bands in between the spectrum. Therefore, this spectra is also called discontinuous spectra. Now, difference between emission spectrum and absorption spectrum. Emission spectrum is obtained when radiations emitted by the excited substance are analyzed in a spectroscope, whereas absorption spectra is obtained when the white light is passed through a substance in gaseous state or in solution form and the transmitted light is analyzed in a spectroscope. In emission spectra, it consists of bright color lines separated by dark lines, whereas in absorption spectra consists of dark lines in an otherwise continuous spectra. So if we observe the emission and absorption spectra of the same substance, say barium, so the difference between the emission spectra or absorption spectra of the same substance is that where the dark line is present in the emission spectra, in the absorption spectra of same substance there present is the color, and the color lines in the emission spectra become black color in the absorption spectrum of the same substance. Now emission spectrum of hydrogen atom. So when hydrogen gas at low pressure is taken in the discharge tube, and the emitted light on passing electric discharge is examined with the spectroscope. The spectrum obtained is called emission spectrum of hydrogen atom. This spectrum consists of a large number of lines which are grouped into different series named as. So please learn this series. Lyman series, when electron falls on the first shell from any other outer shell, but when the electron falls to the second shell from any other outer shell, the series is called Balmer series. When the electron falls to the third shell from any other outer shell, the series is called Paschen series. And when the electron falls on the fourth shell from any other outer shell, the series is called bracket series. And when the electron falls on the fifth shell from any other outer shell, the series is called Pfund series. And when the electron falls at the sixth shell from any other outer shell, then the series is called Humphrey series. So emission spectrum of hydrogen atom. So let's try to understand this by an animation. Here we are representing the various shells by straight lines so that we can understand how the electron falls. This is the first shell, second shell, third, fourth, fifth, sixth and seventh shell. So whenever electron fall from any shell but come back to the first shell only, then this series is called Lyman series. But when the electron falls from any shell but come back to only second shell, then the series is called Balmer series. Similarly, when electron come from any shell but come back only up to third shell, then the series is called Paschen series. Similarly, when the electron jump from any other shell but come back to only up to fourth shell, then the series is called bracket series. Similarly, when electron come from any shell but remain at fifth shell, it is called Pfund series. And when electron come from any shell but remain at sixth shell, it is called Humphrey series. The important thing which we have to learn about this series, that the shell at which the electron falls at last, that is N1 for Lyman series equal to 1, N2 for Lyman series will be either 2, 3, 4, 5, 6. That means electron can fall from any shell. For Balmer series, N1 value that is equal to 2. For Balmer series, the value of N2 will be either 3, 4, 5, 6, 7. For Paschen series, the last shell at which the electron fall, that is N1 for Paschen series equal to 3, and N2 for Paschen series will be either 4, 5, 6, 7. For bracket series, the value of N1 is equal to 4 and the value of N2 is equal to 5, 6 or 7. For Pfund series, the electron last fall on the fifth shell, therefore N1 is equal to 5 and N2 is equal to 6 or 7. For Humphrey series, the N1 is equal to 6, that is the shell at which the last electron fall, and N2 will be equal to 7, 8, 9 or anything else. So limiting line, the limiting line of any spectral series in hydrogen spectrum is the line when N2 is equal to infinity. That means electron is falling from infinity, from any spectrum. Number of lines formed when electron jump from nth orbital can be calculated by using the formula that n into n minus 1 divided by 2. By using this formula, we can find out how many lines will be formed when electron jump from any shell in a given series. Rydberg give a formula to find wave number and wavelength and frequency of these radiation which are found by the spectrum in different series depending upon the value of n1 and n2, and is known as Rydberg formula, which is equal to 1 upon lambda equal to wave number and is equal to r 1 upon n1 square minus 1 upon n2 square, where r is called Rydberg constant and n1 is the last shell at which the electron fall and n2 is the value from where the electron is falling in a particular series. There are two values of Rydberg constant. First is 10.9678 into 10 to the power 6 meter inverse and 109678 in centimeter inverse. Now in normal cases we are using the value in meter inverse so that our wave number or wavelength which we are going to calculate use this formula can become in meters. So the first value we are commonly used. Now this table again we are going to study so that we can understand what will be the n1 value for different series and what will be the value of n2. Lyman series is visible in ultraviolet rays, and for that n1 is equal to 1 and n2 is equal to 3, 4, 5, 6 so on. In Balmer series which is visible in visible light, and for that n1 is equal to 2 and n2 will be 3, 4, 5 or 6. In Paschen series it is visible in infrared and n1 value for Paschen series is equal to 3 and n2 value may be 4, 5, 6 or 7. For bracket series it is visible in infrared region, and for that n1 value is equal to 4 and n2 value will be 5, 6, 7, 8 so on. For Pfund series it is also visible in infrared region and for that n1 is equal to 5 and n2 will be 6, 7, 8, 9. We also have to remember sometime it will say second line in Balmer series and sometimes they say first line in Balmer series. So let's understand the first line or second line in different series means. So in Lyman series the first line means that n1 will be equal to 1 and n2 is equal to 2, and the second line in the Lyman series means that n1 is equal to 1 but n2 is equal to 3. For the third line in Lyman series means that n1 remain 1 but n2 is equal to 4. For the fourth line in Lyman series means that n1 is equal to 1 but n2 is equal to 5. So for Balmer series n1 always remain 2, but for the first line n2 will be equal to 3 for Balmer series. For second line in Balmer series n2 is equal to 4 and n1 remains 2. For third line in Balmer series and n1 remain 2 but n2 become 5. So this is the first, second, third line in Lyman or Balmer series means. So that will be useful in numericals. Now numerical based on Rydberg formula. In first numerical, calculate the wavelength of second spectral line in Balmer series. The solution is that the second line in Balmer series means that for Balmer series n1 is equal to 2 and for the second line n2 is equal to 4, because from the second line means the electron in Balmer series come from the fourth shell. Now using Rydberg formula, 1 upon lambda is equal to r into 1 upon n1 square minus 1 upon n2 square. So on putting the values here we are using 10.9678 into 10 to the power 6, the value for Rydberg constant, because we want that our answer directly come to be in meters. So on putting the values, the 1 upon lambda is come to be 10.9678 into 10 to the power 6, 1 upon 4 minus 1 upon 16. So on taking the LCM and solving, the value of 1 upon lambda is come to be 10.9678 into 10 to the power 6 multiplied by 3 by 16, and on solving it, the value of 1 upon lambda is come to be 2.056 into 10 to the power 6 meter inverse. But we have to calculate the value for lambda, so we take the reciprocal of this value. So the lambda is come to be 1 upon 2.05 into 10 to the power 6, and the answer is come to be 486.27 into 10 to the power minus 9 meter. So by taking this value 10.9678 into 10 to the power 6, our answer directly come in meter, and we can also convert into nanometer. So because 1 nanometer is equal to 10 to the power minus 9 meter, so our answer can also be written as 486.27 nanometer. For the second experiment, calculate the wavelength, frequency and the energy of the spectral line in Lyman series corresponding to n2 is equal to 3. So for Lyman series we know that when n2 is equal to 3, that means the line is second in Lyman series, and for Lyman series n1 is equal to 1 and for second line or n2 is given as 3. Using the Rydberg formula, the wave number is equal to r into 1 upon n1 square minus 1 upon n2 square. So on putting the values and solving it, the answer for the wave number is come to be 9.742 into 10 to the power 6 meter. Now we have to calculate the wavelength, which is reciprocal of wave number, because both are inversely proportional to each other. Therefore wavelength is equal to the reciprocal of the wave number, and on putting the value, the wavelength is come to be equal to 1.026 into 10 to the power minus 7 meter. We can convert it into nanometer also, and in nanometer it come to be 102.6 into 10 to the power minus 9 meter, or equal to 102.6 nanometer. But this is not a necessary condition that you always have to convert into nanometer. You can left it up to meter also. Now for frequency, we know that nu is equal to c upon lambda. So on putting the value of velocity of light and wavelength and dividing them, the answer of frequencies come to be 2.92 into 10 to the power 15 second inverse, or we can also write 2.92 into 10 to the power 15 hertz. Energy can be calculated by using the formula h nu by the Planck quantum theory, where h is the Planck constant having value 6.63 into 10 to the power minus 34, and the frequency we have calculated 2.92 into 10 to the power 15. So on putting the value, the energy of the spectral line is come to be 19.35 into 10 to the power minus 19 joules. Now the next numerical, third, the spectral line in Lyman series of hydrogen atom has a wave number of A2000 centimeter inverse. What transition is correspond to this radiation? The value of here Rydberg constant is already given 109600 centimeter inverse. The series is Lyman, so we know the value of N1 and we have to find out the value of N2. So the solution is that for the line in Lyman series N1 is equal to 1. Wave number here given as A2000 centimeter inverse. N2 we have to calculate. Rydberg constant RH is also given 109600 centimeter inverse. So here second line is written by mistake. Now using Rydberg formula, the wave number is equal to R into 1 upon N1 square minus 1 upon N2 square. So now putting the values, and 1 upon N2 is come equal to 1 minus 0.784 and values come to be 1 upon N2 square is equal to 0.2518. Taking the reciprocal, the N2 square is equal to 1 upon 2518 which is equal to 4, and on taking the square root of 4, N2 is come equal to 2. The next numerical, calculate the wavelength of a limiting line in Balmer series. So this numerical you have to try yourself. Hint for the numerical is that for the Balmer series N1 is equal to 2 and for the limiting line means that N2 is equal to infinity, and we know that 1 upon infinity is 0. So now we have to calculate the wavelength using the Rydberg formula, and the answer is come to be 3.649 into 10 to the minus 7 meter. Next numerical number 5, calculate the wavelength of spectral line when the electron in a hydrogen atom undergo a transition from energy level 4 to energy level with n is equal to 2. This numerical also you have to do yourself. Hint for the numerical is that in this question n1 is given 2 and n2 is equal to 4, and by using the Rydberg formula you have to calculate the wavelength. The answer is come equal to 4.86 into 10 to the minus 7 meter, or you can also convert into nanometer and it comes to be equal to 486 nanometer. So practice these numericals yourself. Study the topic discussed in this video and do practice of numerical based on Rydberg formula. In next video we will study the Rutherford model of atom, its drawback, Bohr model of atom, its drawback, and the numerical based on them. Please like and subscribe the channel for the latest update. Thank you.